All right. Hello, everybody. Welcome back to our conversation about acid-base stoichiometry, titrations, equilibrium. Feels like a never-ending conversation, but that's because understanding fundamentally how weak acids and weak bases behave, how they react, and how they can form buffer solutions is incredibly important, especially if you're moving on into the biological sciences. So we are going to, in this video, continue our conversation about titration curves with an emphasis on titration stoichiometry. So in our last video, we went over why titration curves are shaped the way they're shaped. So it was kind of a conceptual walkthrough of why a titration curve behaves the way it does. And now we're going to prove that to ourselves quantitatively by doing some mathematical calculations, aka some stoichiometry. So let's jump right in with an example about what some calculations involving a weak acid or weak base being titrated with a strong base or strong acid, respectively, might look like. So here in this example, we have a 0.2 molar acetic acid solution. Acetic acid is our weak acid here. And I know this off the top of my head, so I'm just going to go ahead and put this up in the corner. This has a weak acid dissociation constant of 1.8 times 10 to the negative 5. And this solution is titrated with 0.1 molar NaOH. And I didn't provide information about this. Let's assume that we had, like we might in lab, 10 milliliters of this, pipetted into a total volume of 50 milliliters for our titration. So this is looking something like this. We've got our 10 mils of our acetic acid, and then we added some water to that sample to a total volume of 50 mils. Okay, we are also told that the titrant, the strong base, is our sodium hydroxide. This has a Kb that is so insanely large that we can go ahead and presume that the reaction runs to completion, that there's no equilibrium that is really noticeable to us. That is how large these strong acid and base dissociation constants are. So I've got my 0.10 molar NaOH here in the burette. And now that I've got some information about this kind of experimental setup, I am asked a few questions about what's going on here. So the first thing that I am asked to find is the predicted equivalence point. So let's remind ourselves about what the equivalence point means. So remember, chemists are cheap and lazy, meaning we are not incredibly creative when it comes to naming things. So the equivalence point is the point in the reaction where moles of acid is equal to moles of base. Now, what does this mean for us in the context of this titration? This means that the moles of acetic acid in the sample are equal to the moles of NaOH added, with the implication that when these things are equal, all of the acetic acid is neutralized. Okay. Now we could do this fully like this calculation fully with an equilibrium or an ice table if we wanted to, because the acid constant for acetic acid is very, very small. But I know that, or since I have, excuse me, I meant to say since I have an acid constant, but I know that this acid constant is very small, meaning that ultimately, if I apply a small x approximation, the amount of acetic acid, HA, the weak acid, that is present in equilibrium is gonna be about the same as what it was before any kind of dissociation occurred. So we're gonna go ahead and make life simpler for ourselves. And we are going to use the small x approximation conceptually, because we need to figure out the moles of acetic acid that need to be neutralized. So I'm going to call it HA, our weak acid, acetic acid in our sample. And we know that since Ka is pretty small, that the concentration of acetic acid, the weak acid, at equilibrium is equal to the concentration of acetic acid, the weak acid, initially. So I'm not going to set up an ice table because I don't need to figure out X. I don't need to figure out, at least here when finding the equivalence point, how much like hydronium I have. I'm just saying I don't need to think about how much of my molecular acetic acid is now like no longer molecular after dissociation, because this dissociation equilibrium is very favorable toward not being dissociated, very small, reactant favored. If we make this assumption, this allows us to do a pretty basic stoichiometry calculation, meaning I need to figure out the moles of acid that I have so that I can ultimately get the volume of hydroxide solution needed to neutralize. So let's see here. We have this beaker, right, over here. So first of all, we need to figure out the concentration of acetic acid in the beaker, because from there we'll be able to get moles, because concentration is an expression of moles per volume. So let's think about what we were given here. We were given the amount of acetic acid, or excuse me, the molarity of acetic acid stock, meaning pre us putting it into the beaker. So we diluted some of our acid into a new volume. So I've got to use my C1V1 equals C2V2 dilution equation. C2, the new concentration, is what I am trying to find. So I can rearrange this to be V1 equals, excuse me, C2, that's what I want, is equal to C1V1 over V2, where C1, the concentration initially, is my given 0.200 molar. V1 is my initial volume. I gave us this information right here. We pipetted 10 mils over my V2. So this is the total new volume. That's our 50 mils. Right. So this is 1/5 times 0.2, or 0.2 times 0.2, which is 0.04. So I have concentration CH3COOH equal to 0.040 molar. Just a little aside here, a note. I kept my volumes in milliliters because I knew that ultimately my milliliters would cancel. If you had to find a volume, however, just be aware that you need to use your units in liters because molarity is moles per liter. All right. So this is the concentration. And the question is, how many moles? In our 50 milliliters. So we are going to say we have 50 point whatever, milliliters. And I know that there are 0.040 moles per 1 liter of solution. And then if I want to convert my milliliters, I could either just move my decimal over 3 points, or I can do my milliliter conversion. So careful, I want moles and liters cancel. So this needs to be liter. So there are 1,000 milliliters per 1 liter. So doing that operation, let's see here, that's 0.05 times 0.04, 0.002, or 2.00 times 10 to the negative 3 moles of acetic acid. So this is the amount of moles of acetic acid to neutralize. Now, have we answered this question? What is the predicted equivalence point? This is the volume of NaOH added, at which point all of the acetic acid is neutralized. So I need to figure out what volume of my NaOH of known concentration will neutralize this amount of moles of acetic acid. So there's one more step here. Moles of hydroxide required. So if I have 2.00 times 10 to the negative 3 moles of acetic acid, then at equivalence, this is equal to moles of hydroxide, which allows me to take my 0.10 molar NaOH, or 0.1 moles per liter, and figure out moles of hydroxide. Because these are equivalent, this and this will cancel. So I'm taking 10% of that. So that is, oh, hold on, careful, let's check our units here. Moles, those don't cancel. Whoops. So we need to divide 0.10 mole, 1 liter. There we go. Okay, so divided by 1/10 is the same thing as multiplying by 10. So this becomes 0.02, or we drop an order of magnitude, liters. And when we use a burette, we don't typically read liters in a burette, right? We convert to liters. So this is going to be something that, moving all the way over here to write it, put it in liters. I need to now move my decimal over 1, 2, 3. So we expect to add 20 milliliters of NaOH to reach our equivalence point. That is the volume of our titrant NaOH that contains the exact amount of moles equal to the amount of moles of acetic acid present in the beaker. Okay, predicted equivalence point. Up next, in our next video, we are going to look at how we might calculate the initial pH. So just for reference, I am going to put our Ka of acetic acid up here. So let's figure out what's going on in our next video. So see you for part B in our next lecture recording.